here, is that okay? So write down any, okay, so let's say n is equal to 5, whatever, 5. Okay, so let's say we write down, okay, let's say we write down any 5 integers, any 5 integers, whatever. Give me an integer. 3, okay, 3, and then 7, okay, good, and then 10, okay, good, and then 11, yeah, and then you 13, okay, it can be the same, okay, but let's say this, okay, so this is in increasing order. You don't need to have in increasing order, but don't worry about it. So we are claiming that there must be a contiguous sequence such that the sum is a multiple of 5. So we can find a contiguous sequence, okay, contiguous sequence such that it is a multiple of 5, such that the sum is a multiple of 5, is a multiple of 5. Of 5. So here we use n, okay? Okay, so in this example, so it can be very easy. You can find 3, 7. 3 plus 7, okay, it is a multiple of 5. Okay? You can even find 10. Okay, 10 itself, it is also a multiple of 5. Is that okay? You can also find 3, 7, 10. Okay, this is 20. So are there anything else? Maybe not. Okay. So these are some ways that we can find a contiguous sequence such that the sum is a multiple of n. Okay? But of course, you can change it. For instance, let's change it to 11. So we can have two of them to be the same, whatever. Okay, then this one no longer becomes a multiple of 5. So we can clear it. And then what else? So these two are originally a multiple of 5. Okay, let's change it to 4. Okay. Let's change it to 4. And then, yeah, there is no multiple of 5 anymore. Okay? Okay? Is that okay? But still, let's see. Let's see if we can find a prefix sum. Let's see if we can find a contiguous sequence whose sum is a multiple of 5. Let's see. Yeah, let's see. Anyone? 18, 19, 23. The last 3. Yeah, thanks. Last 3. 11, 13. It is it. It is. Okay. Okay, so let's avoid this last 3. Let's change it to 2. Okay. So the last 3 does not add up. How about this case? Yeah, you add all of them. Let's add all of them. So you 2, 13, 24, 31, 35. Is that okay? So how do we prove this? So again, we can use prefix sum to help. Okay, so here, let's see. So let's write down the prefix sum here. So you have a 4, 11, 22, prefix sum, 33, and 35. Okay. Is that okay? Now, either you have found a multiple of n here, which means that there is some prefix which adds up to a multiple of 5, and then you are done. Is that okay? Okay. Or, let's say you don't find any multiple of 5. Let's change it to 1. Let's change it to 1. So this becomes 34. Okay? Now you don't find any multiple of 5. Then what shall we do? This time, let's take the modulo of 5. Let's take the remainder and see what will happen. So this remainder is equal to 4 if you divide it by 5. Is that okay? This remainder is 1, this remainder is 2, this remainder is 3, and this remainder is 4. Is that okay? Okay. And then we must know that 2 of them must have the same remainder. 2. Because what can be the remainder? The remainder originally you can be 0, 1, 2, 3, and 4. Am I correct? but you don't have any 0 anymore because you are saying that there is no prefix that adds up to a multiple of 5. So you don't find any multiple of 5 here. So all of them are multiple of 5 plus 1 or plus 2 or plus 3 or plus 4. They are what? There are 4 types. 4 types. How many numbers? 1, 2, 3, 4, 5. 5 numbers, 4 types. So 2 of them must have the same type. This is pigeonhole principle. Is that okay? In any case, you can always find 2 of them of the same type. Let's say this one and this one in our case. Then what does it mean? This means that the difference between these 2 must be a multiple of 5. The difference of these 2 is a subsequence. The sum of a subsequence. This is you add things up to this one. This is you add things up to the end. And what is the difference? The difference is this part. And this part is a multiple of 5. Is that okay? Okay? Okay, let's give you one more example. Okay, so okay, the other one, and this example is also of, okay, another example. This is not prefix sum anymore, but it has a very similar flavor. So let's do handshaking. So there are a couple of people here. How many people? Doesn't matter, but let's say there are 10 people here around. Okay. At the end of a party, there are 10 people. Okay. Okay, when they say goodbye, they may shake hands or not. But they don't shake hands twice. Okay, so if I say goodbye to him, okay, I just either shake hands to him once or none. Okay, 0 or 1 time. Is that okay? Okay, and then I want to show that, okay, amazingly, no matter how people are shaking hands, there must be 2 persons. They shake the same number of times. You understand my point? So maybe there are 10 people, and then Coco and I are very shy. We don't shake hands with others. So I'm shaking hands 0 times, and he's shaking hands 0 times. Okay, then we have the same number of times to shake hands. Is that okay? Okay, now 10 people. No matter how many times they shake hands, how the ways that they shake hands with the others, then we must be able to find 2 persons. They have the same number of times of shaking hands. Okay, this is very strange, right? But this is a very simple application of pigeonhole principle. Okay, so let's think about it. How many times can a person shake hands with the others? It can be 0, just like me, very shy. 1, 2, 3, up to 9. Very good. So the number of times that we have is either 0, 1, 2, 3, up to 9. Okay? Is that okay? How many different ways are there? There are actually 10 ways. Am I correct? If no one, okay, so we can prove this using 2 different ways. One is simply by a contradiction argument. The other is by pigeonhole. So let's prove it by a simple contradiction argument. So if I'm saying that, okay, suppose that nobody shakes hand with the same time as another person. So what does it mean? So there are 10 different types that they can choose, and there are 10 different persons that we can find. So there must be 1 person shaking 0 times, 1 person shaking 1 time, 1 person shaking 2 times, and 1 person shaking 9 times. Am I correct? Is it possible? Okay. Is it possible? Is it possible to have 1 person shaking 0 times, 1 person shaking 1 time, 1 person shaking 2 times, and 1 person shaking 9 times? Is it possible? No. Why? Why? Because, tricky. If I'm very shy, I don't shake hands with others. Nobody can shake hands with me, okay? Then that means what? That means nobody can shake hands 9 times. I'm not shaking hands with anybody, so nobody get 9. Is that okay? Okay, so this is a contradiction. Okay? Alternatively, you can prove, I hope you understand this. Okay, alternatively, you can prove this by pigeonhole principle. How? So first of all, you find that 0 and 9 are impossible to be together. 0 and 9 cannot be together. So either there is nobody 0. If there is nobody 0, 10 person, you have 9 types, 2 person has to be of the same type. Or there must be nobody with 9. You can have somebody 0. Again, by pigeonhole principle, there are 9 different types, 0 to 8, and there are 10 persons. So there must be two persons shaking hands the same number of times. Is that okay? So you can prove this in very different ways. So you can prove this just by a simple contradiction argument. First of all, if everybody has to shake hands with different number of times, then 1 must be 0, 1 must be 1, 1 must be 2, up to 1 must be 9, and then it is impossible. You prove that. So this is one kind of proof. Done. Or, alternatively, you change the ordering of the argument. You first say that, okay, you cannot have 0 and 9 together. So there are two cases, proof by cases. Case 1, there is no 9. If there is no 9, then there are 9 types, and there are 10 persons, so 2 persons have the same type. Okay? The other case, case 2, you have no 0 but 9. So there are also 9 types, 10 persons, so 2 persons have to have the same type. Is that okay? So pigeonhole principle, that's it. Okay? Okay, okay, so these are the hard examples that I forget. One final question. I hope that this is becoming very easy for you. Okay. So we have a standard chessboard this time. So standard chessboard is 1, 2, 3, 4, 5, 6, 7, 8. And then you have 1, 2, 3, 4, 5, 6, 7, 8. So you have a standard chessboard. So this chessboard is 8 times 8. Okay. So we are going to place rooks to it. So we are going to place. So we are not playing a game that is standard. We are just crazy. Okay. We collect 33 rooks. So rooks is attacking in the horizontal and also the vertical and the horizontal way. Is that okay? So if you place a rook here, so a rook looks like this in the international chessboard, it looks like this. Okay, so it looks like a castle. Okay, but it is called a rook. Okay. So suppose that we place 33 rooks in these 64 squares. So in these 64 squares, we claim that we can always find 5 of them non-attacking. So we want to show that we can find 5 of the rooks that we have placed that they do not attack each other. So what is meant by non-attacking? So if I have a rook here, and then if I have a rook here, then they are attacking each other. 2 rooks on the same row or in the same column, they are attacking. But if I have a rook here and a rook here, they are not attacking each other. Is that okay? So it's not like queen. So they do not control the diagonals. They control only the verticals and the horizontals. Is that okay? Now, so here it says that no matter how you place these 33 rooks, so 1 rook in 1 square, okay, you cannot have, you cannot put all the 33 rooks in the same square. So it is not possible. Okay, so you can put 1 rook in 1 square. You find 33 squares and then place the 33 rooks there. And then after that, you can take away 28 of them so that 5 remains. And then these rooks will not attack each other. Is that okay? Okay, and then hints. Okay, I'll give you a hint here. So we are using the generalized pigeonhole principle. So the general version of the pigeonhole principle. So let me give you a hint. So this 5 is a magic number. That means that after you place these 33 things, one of the hole has 5 roots. If a hole has 5 roots, and then we hope that the same hole, if roots are put in the same hole, then they are not attacking. Okay, so this question is it possible to define holes such that in each hole the roots are not attacking? So how do you, what do you call defined holes? So let me give you an example. So I can put all the diagonals, I can relate all the diagonals together. So these are the diagonals. Is that okay? I can put all the squares in this diagonal into the same hole. If there is a rook here, I'm going to mean that I am putting 2 rooks into this hole. Is that okay? Okay. So in a sense, I can have 8 rooks here, putting here, and then they are not attacking. Okay. This is my first hole. So can we create more holes so that it works? Any idea? So this can be, let's call it hole 1. Hole 1. This is the first hole. Hole 1, hole 1, hole 1, hole 1, hole 1, hole 1. Is that okay? This is hole 1. Okay. Are there any other squares that have non-attacking property? So let's take it for this square. Can I be a little bit more greedy to include more things inside? Yeah, I leave it up to you. Let's think about it. So we have still some time. Let's think about it. So this is rook. This is hole 1. So you have the first hole. This is the diagonals. If rooks are put on the diagonals, then each rook will be placed into this same hole. So I may have another type of hole, I may have another type of hole, and then I may have different types of holes, such that if there are 33 rooks that push into the hole, we will find one of them contains 5 or more. Maybe this one must have 5 plus rooks inside. Okay, so let's guess how many holes are we going to have? Can we have 10 holes? If we are having 10 holes, what will happen? So in 10 holes, then on the average, we may have 3, 4, right? You don't get a 5, okay? Well, 10 holes is not that good, okay? Right? 10, eh? No, 10. Yeah, 10 holes is not that good. We have 33 rooks only. It's not like 64, okay? 10 holes, 8. Is 9 holes okay? 9. 9. On average, you can have, right? 9 times, yeah, is 9 holes okay? 9 holes not okay. Okay, no, because we can have 4, 4, 4, 4, 3, right? So some of them 3, some of them 4. You don't guarantee 5. How about 8 holes? Is 8 holes okay? Yes, okay, good. 8. Yeah, 8 by 8 looks like 8. Okay, good. 8 holes. So the first one is the diagonal. You can design your own holes. Okay, what to be put? Now this is how I'm going to put. Because I'm lazy. Okay, this is the lazy property that helps me to get a solution that I treat it as simple. So the first one looks like a diagonal. Okay. Now let's get the next one that also looks like a diagonal, but we don't have a diagonal anymore, right? But this looks like a diagonal. Right? This looks like a diagonal. They are not attacking, right? They are not attacking. But then what? But then there are only 7 of them. Can we be a little bit more greedy to include one more square? Yes, of course, this one. Am I correct? Is it okay? This one. This is my second hole. So my second hole is dot, 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 and then dot. Is that okay? I can have a third hole. Third hole is what? Again, lazy. This is my third hole. And then what else? I can have this one and this one. Is that okay? This is my third hole. So my third hole is dot, 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 dot. Okay? Is that okay? So I can create the 4th hole, the 5th hole, and then all the 8 different holes. Okay? And then you will see that all the rooks in the same hole, they are not attacking. 33 rooks, 8 holes, one of them must contain 5 or more. So you can have 5 or more rooks not attacking each other. That's it. Okay, pigeonhole principle, usually it helps us to get a very simple proof. But the most difficult part is how do you get the hosts and how do you get the pigeons? Okay, so usually the pigeons is easy to find. The number of holes is easy to guess. But what should be put into each hole? It depends on the problem. It depends on what kind of properties that you want. Here, we want what? We want that for rooks in the same hole, they are not attacking each other. Okay, in a previous example, when we select 51 numbers from 1 to 100, we want what? We want pigeons flying into the same hole, one divide the other. Is that okay? So this is the key idea of how you define holes. Okay, and then in the very, very hard example of the subsequence example, if they are in the same hole, they have the same type, the same the length in the longest increasing subsequence and the same length in the longest decreasing subsequence. So in that case, we get a contradiction. In the same hole, they have the same type, and then we hope to get this as a contradiction. So when we use pigeonhole principle, usually the hardest part is not about counting the number of pigeons or counting the number of holes. It is to design, okay, how to design the property that you need to maintain for each hole. Okay, if you bear this in mind, then usually you get the right way. So perhaps, okay, we don't have an assignment given to you yet, but let me give you another simple example that I hope you can try it at home. This time, again, you have 1, 2, 3 up to 100. And this time, you are still selecting 51 numbers. Okay? And then you want to show that there is a way to find, it's not any. So for any 51 numbers that you get, you can find out two numbers, let's call it x and y, such that their greatest common divisor is 1. So that means that they have no common factor. Any 51 numbers that you select, you can always find 2, such that they do not have any common factor. Okay, think about this. Okay, and that this is an exercise in your next assignment. Okay, okay, that's all. Okay, so we will have our tutorial on Wednesday, and then talk about the exams, and then if we have time, we will talk about the combinatorics. Okay, that's all. Thanks.